Hello everyone, this is Dr. D. Arunbabu. Currently, I am working as an assistant professor in the Department of Chemistry at MITS, Madanapalli Institute of Technology and Science. So I have a PhD in chemistry from Hyderabad Central University. Then I had postdocs from like University of Waterloo, McGill, and Concordia. Right now, I'm working here since 2011. So today, as a part of like lecture series, chemistry lecture series, we'll see about polymerizations, right? So polymerization, right? So before we go to a polymerization, we'll first see what is a polymer. Polymer is obtained from a monomer, right? Let's start with a basic polymer, which is right a styrene. I'm just going to draw a polystyrene structure, right? So polymer, this is a monomer. When you polymerize it, it polymerizes into a polystyrene, right? So you start with styrene, right? And you can polymerize it into polystyrene, right? So whatever I write here is what we call a polymer structure, right? So this polymer, this monomer, we call this one styrene, which is a monomer, is getting repeated multiple times, right? So we end up with polystyrene, which is a polymer, right? So this is a polymer reaction. So this is particularly, it is called as addition polymerization or free radical polymerization. You can prepare this one, right? So I'm going to explain what is right. So based upon the mechanism, polymerization is classified into addition, right, and condensation polymerization, right? We can call this one. In the addition polymerization, you have something called free radical polymerization. Free radical polymerization. You have cationic polymerization, cationic and anionic polymerization. You have different types of polymerization, right? So these are some of the examples of an addition polymerization. A condensation polymerization, right? Yeah, it's named as it is, condensation polymerization. We'll talk about today. We'll just focus on the like free radical polymerization using a free radical initiator using thermal initiation, right? So we'll talk about this one. We'll take an example of a basic monomer, which I can draw like this, CH2, right? All the vinyl monomers, for example, they undergo free radical polymerization. So I have drawn you a vinyl polymer, right? So this is the general structure of a monomer. It undergoes a polymerization. We are using an initiator, right? So the typical initiator will go like this. It is having a structure very much similar to this one, right? So it is a peroxy monomer. It is having peroxy group which can undergo thermal degradation to start an initiator, right? So you're having an initiator, right? So when an initiator reacts, when you heat up, right, around 70 degrees Celsius, right, 70 degrees Celsius and above, it breaks down, it undergoes a homolytic cleavage and it breaks down like this and it forms an initiator, right? So it forms an initiator radical, right? I'll just draw the initiator radical like this. So the asterisk resembles, it is a free radical, maybe it's a very fast, right, powerful electron, right? So I'm just gonna represent a free radical in this manner, right? So you have O minus, K plus, and SO, right? So it is undergoing an homolytic cleavage, right? So this is an initiator. This is where all the reactions are. So the initiator attacks a monomer, right? So a monomer undergoes a homolytic cleavage, right? I'm going to just erase it down. So this is the mechanism of initiator breakdown. Once the initiator has formed, right, the initiator attacks the monomer to form a polymer, right? So here the initiator attacks here. So initiator attacks this one, this group, and this double bond is broken here, right? It undergoes homolytic cleavage, and this homolytic cleavage is, this step is what we call initiation step, right? So this polymer, this is the initiation step, right? It is initiated by initiator. You're having an initiator, right? So this is an example. This is called, right, potassium persulfate, right? So this is a, right, formula of this molecule which is undergoing initiation. So this is called thermal initiator, right? So you're having potassium persulfate undergoing initiation. It produces a radical, right? So it is basically form like this. So initiator is attached with this monomer, and it is no more a right initiator. Now the initiator radical is shifted here, right? So you're having an initiator radical here, and this is now to ready and form a bond with another monomer, right? So another monomer comes in close proximity, then it starts reacting. So you have this one, right? Another monomer. There is a right reaction between the initiator radical and this one, right? So whenever the bond is broken, it is made up of two electrons, right? So one electron reacts with another electron and it forms another bond, right? So this step is what we call initiation, and it keeps on adding monomers, right? Let's say it's a step growth process, it's a stepwise process. Finally you have a polymer, right? So a polymer structure, I'm going to just draw like this. So after series of reactions, you're having a polymer very much like this. So you're having a polymer very much like this, right? So you have initiator, you have, right? So this one has grown m times. Let's say we'll give a number m times it has grown, right? So you're having m times it has grown. Now, right? So you're having another, right, initiator molecule is here, right? So you're actually, you can see here, so CH2, right? So this free radical, you can see this polymer is a growing chain, right? It has grown m number of, right? This group is actually added to the polymer chain. Now the polymer chain is growing. Now it can react with another, right? No growing chain. Let's say you're having another chain, right? Let's say this is, this goes like this, right? So let's say you have another chain that is growing in this fashion. So it's also having a free radical, right? And it is having a repeating unit, something like this. So let's say it's another growing radical. It is having, right? So let's say it is m plus 1. So this one is m minus 1, let's say, right? So when these two react, right, and the polymerization can terminate, right? So this is called a termination reaction. So how long a polymer chain can grow? It can grow until it is terminated. So there is no control in this reaction. So this one is, that is the reason why it is called as a free radical polymerization. So you're having, right, so this name, free radical polymerization, that is the name of this one, right? So since it involves, right, free radical polymerization, so since it involves a radical that has no control, right? So this can continue, once two growing chains meet, they can terminate and produce a polymer, right? So I'm just gonna write this particular structure, right? So you're having CH2 here, so so you're having, m plus 1, let's say this is m and this is 1, and, right, so these two collide, right? These two meet and form a chain, right? Let's say m and m plus n is combined, it has produced this one, right? So it has produced this structure. Let's say you're having this one and both of them combined, right? So this is what we call a dead polymer, the polymer, right, that can never be grown again, right? So this is what we call a dead polymer, right? So this polymerization, right, is the mechanism ends when a polymer is dead, anymore it cannot polymerize. So this is what we call a dead polymer. Is there a way that a polymer can be alive? Yes, right? If you follow something called controlled radical polymerizations, if somebody is doing controlled radical polymerization where they've used copper catalyst and very, right, strict and very strict conditions like no oxygen, so you can make it happen, right? So what are the other techniques that can right, help us to control the molecular weight, right? That is called ATRP. The other one is called RAPT. So these are the techniques, right? We call them as controlled radical polymerization. You can prepare polymers with a predetermined size and shape. So this is what right, at an example you can read about it. So this is a mechanism of free radical polymerization using which you can prepare any number of polymer having a vinyl group, right? So what is the criteria for a polymer to be undergoing this free radical polymerization? It should have a vinyl group, right? So I'm just going to show this one. So I should have done in the first step itself. I'm just saying you can actually got the idea about this one, how they polymerize. So you're having a vinyl group. Let's say this is a typical vinyl group, right? Double bonded, no molecules, right? So or can be anything. So if or is hydroxyl, then it is called polyvinyl alcohol, right? So this is alcohol group. This is called polyvinyl alcohol. Let's say or is Cl. If or is Cl, all is called as polyvinyl chloride, right? So you have another description, right? So all this, right? You can come with n number of names. If or is benzene, if or is C6H5 benzyl group, then it is called polystyrene. You have n number of varieties. So for a molecule to be undergoing free radical polymerization, it should have this double bond, right? So this vinyl group, right? So all the vinyl monomers, we can actually call it as, right? All the vinyl monomers can be undergoing free radical polymerization, right? So we'll see some of the aspects, right? Of, like, let's say we start with kinetics, right? So you're following this reaction by measuring the amount of polymer formed at each second or each minute, right? We can actually follow this one, right, in polymerization, and we can actually follow the amount of polymer formed. Let's say we can calculate the amount of polymer weight. You can actually, so it's a polymer, we can actually call it as weight fraction, we can calculate, right? So with time, what happens when the time increases, the maximum, right, within 30 minutes of time, most of the polymer will be polymerized, right? Most of the monomers will be polymerized and it saturates after a certain time, right? Still, usually when we do a free radical polymerization, usually we give it a time like 4 hours time, right? So that all the monomers are polymerized, right? So one of the techniques we can use to prepare, right, to conduct free radical polymerization is emulsion polymerization. We can use emulsion polymerization. We can use something called, right, so in the emulsion you have micro and mini emulsion. You can, so this is the most famous technique people use to prepare emulsion polymerization. Is the technique we can use, we can employ free radical polymerization. In emulsion polymerization, right, you take water, then you add monomer, right? Mostly water is taken 3 times the weight of the monomer, right? Usually, right, you are taking, right, 100 ml of water, right, 1/3 should be like 33 grams should be monomer, right? So this is the ratio, right? So this is, you're using water and you are using monomer, right? So you can use any water-based monomers or it can be water, right? Mostly emulsion is good when you are using a water insoluble monomer, right? You are using a monomer that is water insoluble monomer, right? So we can, right, so we call them as an emulsion. It is actually called as water in oil in water, right? You're taking a little bit of oil, you're adding it to the water, then you make an emulsion, like the way when you mix oil and water, right? So with the help of surfactant, you can actually make this happen. You're also using surfactant to prepare a polymerization. You're using surfactant, right, so that it is very nicely emulsified. So when you add all of it and when the temperature is right, you can add, right, an initiator, right? So initiator, I have drawn a structure of initiator. So surfactant can be sodium dodecyl sulfate you're using, right? So this is one of the most famous, right, traditional surfactant. And you can also use initiators like APS, ammonium persulfate, or potassium persulfate. You can use, and you can use any monomer. You can take any monomer, water-based monomer. You can take water insoluble monomers to conduct emulsion polymerization. So this is about this one, right? We have seen the kinetic aspects, right? So mostly, right, this polymerization, within 30 minutes to 1 hour, right? So 30 to 60 minutes, you can actually finish, right? It reaches 90% of the total molecular weight of the polymer can be reached, right? How about molecular weight distribution of this polymerization? When you do this polymerization, What about molecular weight distribution? Right, so how does the molecular weight changes? You can actually see there is a polymer, right? So you'll be having a broad distribution of molecular weight. You can actually see this is molecular weight of a polymer, right? Can be, having a wide range actually. Now you can actually see this is a broader distribution. This is particle, right? This is molecular weight. It is actually numbers, right? So we can call it as population of polymer species, right? So let's say a polymer, right? Let's say we start from 100, right? Let's say it is 1 lakh, right? So this is the molecular weight. It is measured in, right, gram per mole we are using, right? Sometimes it is used. Dalton is another unit, right? So Dalton we can specifically reserve it for proteins and biomacromolecules, right? So we can strictly use grams for the polymers. So a polymer molecular weight, a polymer prepared in using emulsion polymerization, is having a broad distribution, right? The distribution is very broad, right? Do we have a polymerization that is having a very narrow distribution? Can we prepare a polymer with a single molecular weight, right, or a very narrow range? It is possible, right? So broad distribution is typical characterization of free radical polymerization. We can use controlled radical polymerization. Controlled radical polymerization, you can expect polymer to be having a single weight, right? Single molecular weight should be uniform. They say molecular weight MW by Mn, right? So MW is a weight average molecular weight and Mn is a number average molecular weight. So this can be, right, we call this one as polymer dispersity index. We can call polydispersity index, right? If it is 1, then, right, so this it is possible using controlled radical polymerization. It is not possible with free radical polymerization. So controlled radical polymerization is a little bit difficult to conduct, right? So we need a constant supply of nitrogen, and also we need to maintain the conditions very properly. Then only it is possible for us to do controlled radical polymerization, right? So this is the basis of it. Then we'll move to the second type of polymerization, which is called condensation polymerization. So condensation polymerization is typically, right, we have seen, right, only the vinyl monomers will be undergoing free radical polymerization. But what is the criteria for a molecule to be undergoing a condensation polymerization, right? In a condensation polymerization, right, so two monomers will be participating, such as, right, I'm just drawing a basic structure. So let's see the preparation of nylon 6,6, right? So this is prepared using 2 different monomers, right? So the first monomers you'll be preparing, I'll explain you condensation polymerization. What is a condensation polymerization, right? Condensation polymerization involves a liberation of small molecules like water or HCl, right? Or small molecules are eliminated. In the case of addition polymerization, there is no loss of elements. There is no loss of any atoms or functional group right here. So here in the example, right, I'm going to show you what is being eliminated in the condensation polymerization, which is used to prepare nylon 6,6, right? So we are taking 2 different monomers. One is adipic acid, the other one is hexamethylene diamine, right? So we'll take an example of this one, right? So you're having adipic acid, right? I'll just draw the structure of hexamethylene diamine, right? So this is the structure of hexamethylene diamine. You're having NH2. For our convenience, I'm going to just draw it in a very different way so that we can write the monomer structures. So this is called hexamethylene diamine, right, reacting with adipic acid, right? So adipic acid structure I'm going to draw for you, right? So this is adipic acid. So adipic acid is having, right, 4 methylene groups in middle, right? So this is called adipic acid. When these two react, right, you have to heat it up, right? When these two react, the water molecule is liberated, right? So you're having n moles of this one, n moles of adipic acid. So you'll be having 2n minus 1, right? Water molecules will be liberated from this reaction. So when these two react, you end up with this one, right? So NH, CH2, it is actually hexamethylene, 6 times methylene. You're having NH, right? And this hydrogen is here, right? So this hydrogen is gone, this hydroxyl reacts, these two functionalities react, right? And you end up with a peptide bond, right? So this is a bond, right? We all know this one. This is a peptide linkage. We call all the amino acids react and to produce peptide linkage. So let me write the monomer structures. I'll tell you the way to write a polymer, right? So here hydroxyl is reacting from the adipic acid, so we'll keep it outside. So what is the meaning of it? It is ready to react with another H plus, another hydrogen from amine, right? So we keep the hydrogen out. So you're keeping hydrogen outside, you're keeping hydroxyl outside, so that they are ready. So this can react with another adipic acid, this can react with another amine, right? So this is how the polymer is, right? Polymerization is continued, right? So this polymerization produces something called nylon. So this one, the commercial name of this polymer is nylon, and it is having, right, 6 methylene group, 6 carbons, and right, another 6 carbons from another monomer, right? So you're having 4 carbons here, 5 and 6. So 6 comma 6 means 6 carbons here, 6 carbons here, right? So the monomers are having 6 carbons. So you end up with preparing nylon 6, right? So this is an example of a condensation polymerization. So let's compare the kinetics of condensation polymerization and free radical polymerization. Let's say time, we can just plot it. This is polymer, the amount of polymer formed. Let's say it is a weight fraction, right? Percentage weight, let's say, right? In the case of this one, free radical polymerization, this is how it grows, right? The polymerization grows very rapidly. The polymer grows very rapidly. On the other hand, the condensation polymerization is very slow in nature, right? So it grows slowly. It grows very slowly, and it reaches the molecular weight, right? Happen. Sometimes the condensation polymerization can go on for it can go on for 1 week also, 3 days, 4 days, 24 hours, 48 hours, 76 hours, right? Sometimes it can go on 1 week's time also, right? So as the time progresses, you end up with a monomer, right? I forgot to add N here. So it is a must that you should add, right? So N, when you write N in the polymerization, that means it is repeated N times. So we call this N as a degree of polymerization. Right, this will tell you the extent of polymerization. So this is called degree of polymerization. So we can actually predict sometimes molecular weight by multiplying the monomer weight, and the degree of polymerization will give you a molecular weight of a polymer roughly. So this is a comparison of condensation polymerization and free radical polymerization. You can see, right, condensation polymerization is very slow in nature compared to free radical polymerization, or addition polymerization is faster, right? So we can see, right, so this monomers having NH2, right, hydroxyl, they can react, and produce water as a byproduct and end up with this kind of polymer, right? So this is a polymer resulting from a condensation polymerization. So this is an example of condensation polymerization. Condensation polymerization involves the release of small molecules, right? So all the polymers prepared from the condensation polymers, most of them should be thermal polymers, right? Thermosetting polymer, right? So this is a rule of thumb here, right? So thermosetting polymers are prepared using condensation polymerization. What is the thermosetting polymer? A polymer that the mechanical property of the polymer increases, right, upon heating. If a polymer, right, becomes hardened, then we can call that one as a thermosetting polymer. How about a thermopolymer? Thermopolymer, right? Thermopolymer actually, right, it melts upon heating, and this polymer hardens upon heating, right? So this is a basic criteria. All the addition polymers will be thermopolymers, and all the condensation polymers could be thermosetting polymers, right? So this is the basic difference between condensation and addition polymerization, right? We'll give one more example, right? I'm going to show you a preparation of a very special polymer that is used in the bulletproof vesting preparation. So, like, people, right, it can be useful in the people who are dealing the crimes, right, and everything. It was invented way back by a woman scientist, right? She's from Poland, and she has, right, copyright rights, patented this particular polymer, and it was very successful. The polymer's name is called Kevlar, right? So I'm going to just show you a preparation of Kevlar polymerization. For a Kevlar polymerization, you're having two monomers, right? So you're having a monomer called, right, diamino-benzene reacting with terephthalic acid. You end up with Kevlar polymer, right? So you're having terephthalic acid and you're having diamino-benzene, right? So this is the two monomers reacting with like to produce a Kevlar, right? So you're having this functional group, right, and this, right, in the way we have seen as like known the preparation of nylon. So these two react n moles of this one, right? So usually they take equimolar concentration of two monomers. These two react to produce water molecule, right? So water is produced, 2n minus 1 water is liberated from here, and you end up with a polymer, right? We call this polymer as a Kevlar, right? It is a bulletproof polymer, right? It can, it is so mechanically strong. Even somebody, right, shoots you with a gun, this polymer can protect you, right? So this is a bulletproof polymer, right, which is commercially known as Kevlar. So you're using diamino-benzene and terephthalic acid is used as a monomers. These two react to produce this Kevlar, right? I'm just drawing a structure here. Right, so it is also having, right, a peptide linkage. We call this one as a peptide coupling, right? Peptide linkage in biology is very important, right? We're all made up of 20 factorial amino acids, right? All the amino acids react to produce a peptide linkage. So this is a bond of life, right? We can call this one, right? I'll just come back here. So you're having a bit, right? You're preparing a Kevlar, a polymer known for its very unique property. It's a bulletproof polymer. It's very stable and strong, right? Mechanically, very strong polymer is it, right? So I'll keep the hydroxyl outside so that it is reacting, right? So this is how we represent. So this polymer is what we call Kevlar, right? So Kevlar, right? So this polymer, right, is an example of a Kevlar, right, condensation polymerization, right? So we have seen the examples, right, mechanism of addition polymerization, and we have seen the mechanism of condensation polymerization, and also, right, we have compared the kinetics of condensation polymerization and free radical polymerization. So we have learned the basics of addition and condensation polymerization with examples, right? So thank you very much for your kind attention. Thank you so much.